non-malleable extractors and codes for AC0 and affine functions, and this is joined with Shenley. The paper is not out yet, but hopefully in a day or two we'll put it up. All right, so before describing what a non-malleable extractor is and non-malleable codes are, let's start out with some basics. Let's start out with extractors actually. So, to define extractors, we'll need to recall randomness in computation. So these are functions which take in weak random sources and spit out uniform bits. So this is very informal. So let's recall what min entropy is. This is the main way of measuring the randomness of a source. So suppose X is a distribution. So the min entropy of X is it looks at it's the worst case version of Shannon entropy, and it looks at the element on which X places maximum weight. So another way of interpreting this is if the min entropy of X is K, then the probability X equals to X is 2 power minus K. So this is for all X, right? So this is the notion of min entropy that we'll be working with, and sorry, this is the notion of randomness we'll be working with, and so we'll be looking at n comma k sources. So these are X is an n comma k source if it's on n bits, and the min entropy of X is at least k, right? So it places weight at most 2 power minus k on any string. And the first definition of an extractor would be probably to say that, so extractor is a function, say from, so this is the set of all n bits to, for example, suppose you just want to get one uniform bit out. And you'd want this function to work for probably all n comma k sources for some k, maybe polylog. But it turns out that the first well-known fact is that so I'm being a bit informal here to get through the basics. So no extractor for n comma n minus 1 sources. So there's no single function which can extract from all n comma k sources. All right, so now there are various directions in which research progress. So on the yeah, sorry, yeah. So okay, so we'll be dealing. So we'll use statistical distance. So for two distributions, x minus y is just so the L1 distance between half of the L1 distance between. And if it's just bits, then it's just the probability that it's all right. So the way around this was there are various directions. So one is the notion of a seeded extractor. Then there are seedless extractors for structured sources. So a seeded extractor is where you have a source X, which is n comma k, and now you have an additional independent seed Y.
Can you write those in detail?
Sure, yeah. All right. And the guarantee that you would want is that the output of the extractor, so I'll use this for closeness in statistical distance. So this is close to uniform. Similarly, for structured sources, there are many directions. So one very well-studied one is where you have, say, access to more than one source, more than one independent source. So X and Y are independent.
Independent also in the seeded extractor, so maybe.
Right, okay, yeah, that's a good point.
One Y, one X1, X2. Also.
Right, yeah. And they are both n comma k sources. So here we assume that Y is an independent uniform seed. And here both of them are n comma k1, n comma k2 sources. So both of them are weak sources. And you again want a similar guarantee that the extractor of x1 comma x2 is close to uniform. And there are other kinds of.
Obviously, you could just, in the first case, couldn't you just spit out Y? Or
Yeah,
or do we
yeah.
consider Y to be
Right.
expensive? Or is it
No, yeah. So that's yeah. So typically you would want M to be close to the entropy of K.
I see.
So yeah, and
Y to be short.
Y to be short. Good.
You can also condition that the output has Y concatenated to it, and the whole
Right.
together should be just as strong.
You can write it like that.
Yeah.
Doesn't matter.
Yeah. So yeah, as I've said, the notion of a strong seeded extractor is this, that you'd want it to spit out uniform bits even conditioned on Y. So you do not allow the extractor to cheat. Similarly, here there are notions of strongness with respect to the source and stuff like that. All right. So other things that have been studied are, say, when you have just one source X, but you know it's uniform over an affine subspace, or maybe uniform over a variety. Zev has work on it, Zev RV. Or you could assume that the source X has been sampled by some computationally limited device, like a low depth circuit or a space bounded machine. Right? So so these are mainly the directions that have been taken, but recently there has been a lot of work on a quite non-trivial generalization of seeded extractors. So that's what will be the topic of today's talk. So we'll look at non-malleable extractors. So here similarly, you have a source X, which is n comma k, a short seed Y, which you would want it to be short, and it's uniform on d bits. And now there is an adversarial function f from d bits to d bits such that f has no fixed points. So f of y is not y. And now the guarantee that we want is the output of the non-malleable extractor the guarantee that we want is that the output of the non-malleable extractor looks uniform, even conditioned on the output given on a correlated seed f of y and the seed itself. Right? So, I mean, obviously, if, for example, f was the identity function, then these random variables are the same. So you cannot expect this to be uniform conditioned on this, right? Okay, so the non-malleable extractor has to work for all n comma k sources, a uniform seed, and any adversarial function f which satisfies the condition that it has no fixed points. All right.
So usually you think of f as a permutation, or?
For example, if f is the constant function, then it's very easy, right? I mean,
Yeah.
a
So
so
with no fixed points.
yeah,
Or no?
yeah. That seems to be one. That seems to be a hard case, but I'm not sure if.
In cryptography, there is an adversary that picks f, so it can want to do something different than a permutation.
They can map multiple things to the same thing.
Yeah, it doesn't.
Yeah, okay. Just asking what is the motivation, where does it come from?
Oh, the motivation of non-malleable extractor. Oh, so yeah. All right, yeah. So non-malleable extractors came up in cryptography. It was introduced by Evgeny Dodis and Daniel Wicks, and the main purpose was this application to privacy amplification, which I was not thinking of going into, but
You don't have to.
Okay.
If you want.
So basically, we share some big random source. We can
Yeah.
jointly see it, and we want to authenticate a session with a private key.
so there is a public channel, and you're communicating, and you want to get to a uniform string. So if the adversary does not change what you're communicating, then you can just use a seeded extractor. Like one of them picks a seed and uses a strong seeded extractor. But now if the adversary is active and starts changing things, then there is a very nice two-round protocol. Yeah, so yeah, the idea is like in the first round, one of them picks a seed and sends it across, and that's the seed for the non-malleable extractor. And then the outputs are used as keys for a one-time MAC for the second round, where you send actually a seed for the seeded extractor. So it's kind of saying that if the adversary actually changes in the first round, then they both have like independent keys. So the adversary cannot really do anything. And if it does not change, then it reduces to like just using a seeded extractor. So that's kind of the idea.
So f is a deterministic function.
Yeah, f is a deterministic function. Yeah. Well, yeah, it
But
does.
the
Yeah,
probabilistic,
yeah.
don't change anything.
Right. Yeah. Exactly. Yeah. All right.
So you
So-
want to say, I mean, maybe,
yeah.
I don't know.
Yeah. The exists.
You use it later. Does it matter? I mean, that's one definition of non-malleable. Another, which is slightly weaker, is just to say that for every two different
Right.
seeds, it produces independent
Yeah.
outputs.
Yeah.
You
Yeah. I'm not really. But yeah, that's a very.
use this or you use the other.
Yeah, this definition is good enough for the talk. But yeah. But yeah, it's. So as Avi pointed out, so for a strong seeded extractor, essentially, what you're saying is that for almost all seeds, the output. So if you fix the seed and think of the extractor as a function on the source, then if you have for most fixings of the seed, the output of the extractor is actually uniform, because it's just a Markov argument by like summing over all the y's. So the non-malleable extractor is. There's another way of saying that this is a generalization of seeded extractors, because this kind of says there's an equivalent formulation of non-malleable extractors, that there's a large set of seeds, such that any two seeds, so if you look at the functions by fixing the seed, like pick two independent seeds, then the non-malleable, these two functions are pairwise independent, essentially. Is this clear? Like, so there is a large set of seeds. So size of S is like such that for any y1 and y2 distinct in S, both of them are in S, you have that the non-malleable extractor of x comma y1 and is actually close to this. So yeah.
Is this so you can also ask for let's say most of the pairs, as a fraction of the pairs y1, y2 have this property. So this is not the same. This is stronger
There's a
than that.
difference.
It's a
But then it's any strong series extractor would have that.
yeah. So actually, this is actual equivalence. So the actual equivalence is this: that you pick any y in your set S, and the y2 can come from even outside S.
So every pair that touches this set S.
Yeah, exactly.
That's the equivalent.
That's the equivalence. Yeah.
But it's much stronger than saying most pairs.
Yeah. Right. Yeah. I think for most pairs, the permutation will So. So y1 is in S and y2. Right. And okay, so existential results. So by pluralistic method, you can show that seeded extractors exist with seed length order log n. So here, this epsilon, this parameter is called the error. So log n over epsilon, and works for any entropy. And there are, like by a long line of work, we also have really good seeded extractors, which almost get all of the entropy out. Like m is 0.9k, or even you can go even closer. And it's not very hard to use the pluralistic method here to show this. And for non-malleable extractors, it's slightly trickier to show that even they exist. But it's known that it exists for, so the min entropy you require is at least log 1 over epsilon, and the seed length is log 1 over epsilon, log n over epsilon, right? So so excellent constructions of these exist. Pluralistically are. So so we'll be looking at a further generalization of non-malleable extractors called seedless non-malleable extractors. So before that, for explicit constructions of non-malleable extractors, the best known work for so explicit constructions are almost optimal now. So it's known for k, which is and this is the best result is due to Shinley, and it's a lot of recent work and so on.
These of k, so that they can also go down to logarithm.
Oh yeah, sorry. Right. Thanks. Yeah. And so another application of these non-malleable extractors are actually in constructing extractors for structured sources, more specifically for independent sources. So if you can, so the best known two-source extractor for constant error has this same entropy bound, log n, log n. So if you can remove this thing, then it will give you order log n two-source extractors, which is a very interesting problem, I guess. All right, so
So is log n, is that what's guaranteed by the probabilistic method?
yeah. So the probabilistic, related to the Ramsey graph bounds, and so it's actually log n plus order 1. So right. So we'll look at a variant for the generalization. So these are called as seeded non-malleable extractors. So there was a further generalization introduced by Cherakchi and Guruswamy in 2014, which introduced seedless non-malleable. So it roughly corresponds to the analogs of seedless extractors. So for example, for two-source extractors, you'd want a seedless variant which roughly satisfies Okay, so the reason for studying this is actually due to connections to these things called as non-malleable codes, which I'll introduce after getting through, like introducing these things. So, all right, here you would want that the extractor. So now x, maybe again it's better to use x1 and x2, right? So here x1 and x2 are n comma k sources. And so for the rest of this talk, we'll just work with functions which have no fixed points, but actually you need to deal with fixed points, but it's a different issue. So so the length of the output. So you'd want it to be maybe.
You have the bounds on the construction, so like the K and D, shouldn't there be an M in there as well?
Yeah, so M should be
Yeah.
in all of them. Also the lower bound and the upper bound. M is almost K.
Yeah, m is almost k.
So you get all the entropy out.
Right. Yeah. So. All right, so so this definition is clear, right? So now what you do is, here we did not allow the source to be changed, but now both x1 and x2 are being changed, and we want a non-malleable extractor which works for these kind of things. Again, using the probabilistic method, you can show that there exists such extractors for k, which is log n.
Why is the fixed points important here? It's not the same problem as before. Because
Well, these are the identities.
Both, yeah.
There will be no independence between the output.
like one of them is fixed and the other not.
Yeah, so yeah, it's actually sufficient for one of them to.
Or they don't have common, or if one of them doesn't have.
Yeah.
So this is analog of the two source.
This is the analog of two source.
Analog
Yeah.
as a structure.
Yeah, so that's the, I'll get to that. That's the topic of today's talk. Hopefully I'll get to it. Okay, so it turns out that it's really tricky to construct these things, and so even when x1 and x2 are uniform, coming up, sorry, yeah.
Maybe
Mhm.
there's something I'm missing. So if all we know about f is that like, f has no fixed points, I guess why why use nmx f of y as an input at all? Like, couldn't you just pick any y2 which is different than y?
Oh, so you're asking instead of f of y, why don't we have any fixed y2?
That's this definition here.
So, so f roughly corresponds to this adversary who's like trying to create some correlation between like the output of the actual non-malleable extractor and whatever he's trying to learn about x. Or so. So is the question that why can't we just fix this to y2, like a fixed y2 which is?
Or at least say like y2 equals y plus.
Oh, so you're.
one bit or something.
Yeah,
Special.
that's a special case, right? Yeah. Yeah, or as Avishai asked, like just maybe look at permutations. Or right, but in the cryptographic setting, you assume that the adversary who's changing the things has unlimited power. So, at least in the privacy amplification setting, you'd want to deal with arbitrary adversaries. So the thing is, if f has fixed points, it's kind of saying that the adversary is not changing anything on the channel. So that is good for us. And in this application, one has to deal with fixed points to get the codes. But it turns out that you can trade off fixed points to go to, like if you have extractors for slightly lower min entropy, then you can deal with the fixed points. So
we can stick with this definition.
yeah, we can stick with this definition. And so it's not obvious. So none of the seeded non-malleable, at least before the new works, it was not clear how to construct these things even for if both x1 and x2 are uniform. For example, clearly the inner product function will not work, and even like the Paley graph kind of thing, which is actually a seeded non-malleable extractor, doesn't work here. So,
So for example, why does the inner product doesn't work?
so for example, like it's maybe easier to work over FP, and if x, so the inner product is just the product, and then f of x could be like just 2 times x, and g of x could be y, like one would multiply a 2, the other would like divide by 2, or so. And like x plus y, you can change one of them to x plus 1 and the other to y minus 1, and you get back the same thing. So yeah. So the first construction was actually a work I had with David, but it was weaker. It took 10 sources, and so you generalize it to 10, you have 10 different functions, and it used, so it required min entropy which is really large, like n minus little of n, and use sum product theorems over rings. So and the first construction was in a paper with Vipul, Goel, and Shinley, and that actually solved the case for 2 sources, but still requires min entropy which is n minus little of n. So it's open to get it down, but for the applications it's enough to get high. All right. Okay, so now probably I'll get to the point of this talk, which is
So, but
yeah.
that's that's
Yeah.
the best now
yeah. So
for 2 sources.
for 2 sources, yeah, this is the best node.
Even
Okay, so
constant rate is open.
I think with so so this is, I'm not sure, but I think one of the sources can be constant rate, but I don't know how to push.
Sources of constant rate.
No, right. Yeah.
What does the probabilistic method say here? The same thing?
Same thing. Oh yeah, so another motivation for, all right, so another thing is the error here is ω1, not for this, but for all subsequent results. So even if you get for this entropy error, which is 2 power minus ωn, this will give you again two source extractors for log n min entropy. So this is another way of going there. Yeah.
So the usual two source extractors, they give bipartite Ramsey graphs. So do these give any nice graph?
Yeah. So Raghu actually observed that this gives a very, I think maybe it will need slightly stronger parameters than this, but so I think what it gives is, if you have a bipartite graph, and so the corresponding bipartite graph for this, and then you look at a constant number of vertices from the left and the right, like look at all pairs of such, and then the frequency of the subgraphs is roughly what you would expect.
This is equivalent to this non-malleable.
So this implies that I have to check if
So all these results work also when one of them has no fixed point of the functions I mentioned.
So this works.
It's enough.
So these things are very robust. It goes through this alternating extraction thing, and most of the things work. But for this, I think it was trickier. So all right. So today's talk will be. I should introduce non-malleable codes before. So maybe I'll do it here. Is this visible? So non-malleable codes arise with applications in tamper resilient crypto. I'll try to give a short, brief example of how to use non-malleable codes here. But so these things are a relaxation of even error detection codes. So roughly the model is this, that you have a message M, and so this is a randomized function. And now you pick a function f from some family f. So the thing is, so non-malleable codes looks at the change of the code word as some tampering function acting on the code, and its goal is kind of to look at the most general class of functions that you can handle with still providing some kind of guarantee. So
the one we are most used to is changing some number of bits.
Yeah, exactly.
So now we want to avoid it different ways.
Or even change a lot of bits. So if you want to add like an arbitrary offset, then you can actually, there are error detection codes called AMD codes. It's a very simple construction, and you can actually detect errors. But for example, error detection is weak in the sense that if your class of tampering functions is just the fixed functions, like it fixes each code word to a single thing. So it could potentially fix it to a valid code word, and then you do not know if there was any change. So this is, say, some C prime. So this is the entire process of the encoder working, and there's some tampering going on. Then you decode it back. This is a deterministic function, and so you get M prime. So M prime is probably a distribution on the message space, right? So you have M. We encoded it using a randomized encoder. It's a distribution of over the code words, and now f of c is also a distribution on the code words. Now you get by decoding, you get a distribution back on the state of messages. And the first guarantee you'd want is that if f is actually the identity function, then you'd want to get m prime equals to m. So that's the first guarantee, that then m prime equals to m. And the other thing is extreme, in the sense it's not what you want from a code. Is so you'd want that, say, if f is not the identity, for example, let's look at the extreme case when f has no fixed points, then you'd want so ideally you'd want either to get back the message, or so let's simplify and just say that you'd want so this decode of f of encode of the message. So this should be in statistical distance close to some distribution df, which does not even, so it's independent of the message m or the randomness in the encoder. So what it's kind of saying is that there's no adversary which can actually fool this system into decoding some message of its choice. So df is some independent distribution.
But maybe you decode it correctly, so it's like you want one of two choices or something?
Right, yeah. So the more technical way of stating this is, so df is actually, so df is actually not just a distribution on the messages, but also this special symbol same. So if it's same, it's like you put in another function, copy here, and you also supply the message. So df is allowed to output a cheat symbol, and this cheat symbol kind of says that it actually decoded back successfully, and then you output m. But
the condition of not outputting m, it should be independent of m?
yeah, the probability should be.
Just for any f, or just f's that are not fixed points? Or?
How for any f, yeah.
For any f, if you already do this, then it's for every f.
Yeah, for every f.
Include
No,
case one.
yeah.
Well, case one is still have to put that.
Oh, yeah. Right. Okay. And so these things are used.
For which you can, or maybe if you give
Right.
the last family, when can you do it?
Right. Yeah. So existentially, it's known that if the family size is bounded by, then there exists NM codes. So the rate of the code is the usual, like if it's from k bits to n bits, then with rate 1 minus alpha, and so this epsilon is called the error.
Somebody says, well, this code is taken. What is it?
Oh, so it's the space of functions. It's yeah.
So here you are not trying to save on the randomness of the
No,
code
yeah.
procedure.
No, yeah. So, and there's this really nice connection between seedless non-malleable extractors and non-malleable codes.
So just a second.
Yeah.
This statement is existential.
Yeah,
So
Pro-
just
probabilistic,
accounting,
yeah. Yeah.
Non-malleable encryption solves this in some way.
You mean you can?
Like if this is an
But in
encryption,
non-malleable encryption, you assume the adversary is bounded. This is information theory.
Yeah, it's in statistics. Yeah.
but then the F is computationally bounded. I mean, I think if F is polynomial time and under computational assumption,
Right.
this is exactly
Yeah,
non-malleable encryption decryption.
Yeah. Right.
The definition there, I think, is a little different because you don't want to, it's not about the,
it's
it's
similar.
not about the code, no, but there it's not about the code. You don't want to be able to generate related. The non-malleable, the definition I know.
But if you could generate a related ciphertext, that would be this F, and then you would decrypt a different message than you thought you would.
then it would not be, okay.
That's exactly the idea.
I see. Yeah.
You're trying to F is trying to simulate a valid code root for a different message.
Yeah.
You wanna
Exactly.
say
Yeah.
that's
Yeah.
hard
Yeah.
for
Yeah.
whatever class of functions.
Right. Yeah. Statistically hard. Yeah. Right. So you had a question.
So M is the size of the message that you decode, right? That you encode.
Oh yeah. So yes. Yeah. M is on k bits and
So the requirement is when you fix F from this family, and when you fix M, if I will do this process, then at the end I will get some distribution which is independent.
so yeah. So you get the distribution which does not depend on what M you started for. With.
Yes, okay. For M fixed and F fixed,
No. So M is not only F. So the distribution is just dependent on F.
right. But the randomization is in encryption. You start with an F,
Yeah.
and then
This
you
is
want
true
the
for
F.
every M. The statement too is
Yeah,
true for every M.
So one well-studied class of family is this split state model. Where if this is the code word, then the tampering function roughly works with like f acting on this half and g acting on this to get c prime. So f is allowed to be any arbitrary function on n over 2 bits, g on any n over 2 bits, and you get this. So it's easy to see that it's bounded and there exists. And so now there are codes in this model known with rate 1 over log n, and yeah, it's still open how to get constant rate.
This you're not talking about explicit.
Yeah, I'm talking about explicit now. Yeah. So
How it was existential, but
Yeah.
for this very structured.
very
kind of-
yeah, right, yeah. And most works on how to many works on how to construct non-malleable codes actually come through constructing these seedless non-malleable extractors. And roughly the connection is this. So So again, this is Cherepchi and Guruswamy. So they roughly show that if you have, for example, if you have a two-source seedless non-malleable, if you have an extractor of like this, then it corresponds to, it gives you codes in the split state model. and the encoder of any message is uniformly sample from the inverse of. So look at all the pre-images for which, look at all the inputs for which the non-malleable extractor outputs S, and uniformly sample from this. So, and the decoder is just the non-malleable extractor.
So you need
Yeah.
to have a non-malleable extractor that's invertible in this sense.
Yeah, exactly. So you'd want this to run in time poly mn log 1 over epsilon.
This
So
would work for any model of deterministic sources.
right,
It's
yeah,
a general thing.
it's a general thing. Yeah.
Affine source.
So, and it's not very hard to see that. So this actually, so obviously the first condition is satisfied that you get the identity back, and yeah. So we can quickly look at why this holds. So. Okay, so the condition that, yeah, we can just prove it for any general class of sources. So suppose you have X, and so think of X, so X is say the uniform on n bits, and yeah, because
Full entropy.
it's full entropy. Yeah, exactly. So since you're you're sampling, so the point is, you say, so the target distribution df is actually when you say that you uniformly pick a message and encode it. So you show that anything is close to that, and you pay an extra 2 power m loss. So
that's the assumption.
yeah,
So once you
yeah,
go
this is
down,
the,
that's
yeah,
for every f in f, right?
right, yeah. Assume this works for every f in f, yeah. So this can be seen as so suppose you uniformly sample a message S.
But we need the result should be for every message. Right?
Yeah. So yeah, we'll prove it for a random message and just pay in the error. Yeah, exactly. So then this is so this will be close to S comma some distribution D, which is independent of S. So now this means that this distribution is close to D. For
wait.
yeah,
You have your assumption, and what is this? Now you are proving that this scheme
yeah,
actually is a good code.
exactly. Yeah.
Why?
Okay, so so you pick a uniformly random message, and the encoder is just the inverse of the non-malleable extractor applied on this uniform message. So it's easy to show that this is epsilon close to uniform. So instead of X, you can just work with this source. And now you just plug it in this as well. And the non-malleable extractor, so the encoder is just the inverse image, so you actually get back S. And by our assumption, we know that these both are independent random variables. So there is some distribution D, which is independent of your message S.
But that depends on the littlest one uniform.
Right. Yeah.
How do you deal with fixed points?
Right.
But this statement is
Yeah, so it's kind of like assuming this statement is true, is kind of saying that F does not have too many fixed points.
Well, to use this, you have to assume F has no fixed points.
Yeah, F has,
so
yeah.
there is a
But
family
here-
F for which this is satisfied.
Yeah.
Some
So yeah, you are right. So to prove for, this works for this thing works for families which, or functions which
Like
do not have.
shifts, for example, the identity and everything else has no fixed points.
Right. So, yeah, the actual definition of a seedless non-malleable extractor also has to go through this this copy kind of thing. So that's how you deal with fixed points. So it's kind of saying that.
What is D telling you here?
So D is some distribution which is independent of. So it's kind of saying that these both are independent random variables. So now you can go from a random message to, for all S, it implies that this is a standard lemma one can prove in for statistical distance. So
What for every S?
So for every S, what this implies is that the.
Well, little m is overused. I don't know.
Oh yeah, sorry, yeah, yeah. Right. So if you output t bits, then we pay an error, a multiplicative 2 power t kind of thing. So
You can't have any bad ones, any bad messages.
oh no, this yeah. So this is just a trivial like. So since S is uniform, so it's like 1 over 2 power t times the sum. So each of them. So you know that the sum is bounded by epsilon. So
The main point is that this encoding has to inject a lot of randomness, much longer than the math, right?
and you would want a non-malleable extractor with small error because the rate of the code is t over n. So to get better rate, you would need non-malleable extractors with smaller error.
So you want error like 2 to the minus omega of n to get constant, right?
Yeah, exactly. Yeah. And yeah, so yeah, the thing about this obviously assumes that F does not have too many fixed points. But if F has fixed points, then we are kind of in the good case because just to get non-malleable codes, it's kind of saying that we decode back to the same message. So, but yeah, one needs to be careful about that. All right. So the
So
Yeah.
if you happen to have non-malleable extractors here for lower entropy, can this help you in any way, or because then you don't have to sample uniformly from the pre-image?
right, yeah, to save randomness maybe, yeah. Maybe if it's over some, it should be also easily sampleable, so maybe some subspace or.
Another question, so let's say it's affine sources. Do you need f of x to always also give an affine source?
Okay, so yeah, that's the, yeah,
You will talk about
Yeah, I'll talk about it. Yeah, that's the result of this. So, all right. So let's.
Will you go back to codes, or we will just talk about extractors now that we know that?
Yeah, right.
Just extractors.
I'll just talk about extractors, and the codes will follow by assuming that we can, like, make these extractors nice enough to make it invertible. So, yeah, it turns out that it's really messy to make them invertible, but it works out. So, yeah. Okay. So,
So you only need to from the inverse, right?
almost. Yeah, you need to.
Only is,
No, what I need to remember from
Yeah.
this part is
Yeah.
this is what I need.
Yeah, exactly. Yeah.
to make sure they are not one-way functions.
Yeah, it's mostly it's carefully sampling from subspaces, so that's the only thing we need how to do, or low degree. Okay, so so the first non-malleable extractor. Okay, so let me formally define say affines. So we know what affine sources are. It's a uniform distribution over.
We know, but if anybody does,
Yeah.
it seems that some people may not know.
So
I don't know what enough I know.
Good.
yeah, good. Yeah.
Ask. What do you think?
So it's X is uniform on some affine subspace of. So the entropy of X is K, implies the dimension is at least K. Right, and the other thing is oblivious bit fixing sources. So they are a special case of affine sources, and it's even much simpler. So there are some coordinates which are, so these are uniform and independent bits, and the rest are fixed. So these are fixed. So these bits do not even depend on the random choices of the random bits. So they are fixed bits, and then there are some unknown coordinates which are uniformly and independently sampled. Right. So a very easy extractor just to get one bit is taking the parity of all the bits. All right. Okay. So our first result is.
You probably want to say what's known about this.
Oh, yeah. Okay, so yeah, I should go into that, right? And it's not.
Just that
Yeah.
there are good deterministic extractors.
Yeah.
For this,
Right. Okay. Yeah. So for affine sources, there is explicit constructions for polylog and min entropy, and this is least extreme and also a follow-up. So, and bit fixing sources have been studied even more. So there's a line of work which until recently it was known how to do for linear min entropy, and then Shinley got it down from n from n by root log n to polylog n. And for bit fixing sources, there's a long line of work which gets almost all of the entropy out. So,
but there's still work to be done, right? Because the error is not so great.
right, in the affine case, yeah. Yeah. Right. So we, in this work, we essentially construct non-malleable extractors for affine sources and for AC0 sources. So what does it mean? So the first result is, say, so X is an affine source with entropy at least this, and yeah, for any delta, I think. Yeah.
Any delta less than 1.
Yeah, any delta less than 1. And any affine, yeah, any affine function from
without fixed points.
yeah. So again, for this way of stating, assume A has not too many fixed points, but yeah, so the fixed points is again, so you can, it's a linear restriction on the source, so you can go, so if A of x equals to x, then so just for getting applications without fixed points, this entropy would be enough, but if you want to handle fixed points, this is enough. You go slightly lower, and
So you can handle any of them.
yeah, any, yeah.
And is it natural to restrict A to be affine, or can you ask for this to exist for any A?
Right. So it's natural to ask for. Okay. So it's natural to ask for affine functions because. Yeah. Right. Yeah. Yeah.
But a random function would work for any A if it's an affine.
No. So yeah, I don't know how to show that it exists for any function. So
it's not obviously that it doesn't obviously not.
yeah. So
It's hard to believe, no? But for n.
for any f, right? Yeah. It's
Not any affine, but label graph.
Can this exist?
Extractor for affine sources that's non-malleable against every.
Why it's hard to do
And no, it's hard to believe.
at least the
I don't know.
yeah.
Not so my
You have two restrictions. One is the source and one is the function. I mean, it doesn't have to be the same restriction.
Right. Yeah.
I don't know.
Okay, so and yeah, this is, and it turns out you can do a lot of, so the explicit construction you can play around a lot and finally make it invertible, which gets you the codes. And okay, so maybe sorry.
What's the error?
Okay, so yeah, it should be more specific. Okay, so. And this is
So T is the output length.
T is the output length. Yeah.
Sean, by the way, Avishai complained that it's not good that the speakers will decide if there is a break.
Oh, there will be a break. Yeah.
So
Yeah, I'll just state my
whenever
yeah.
you, yes,
Yeah, because after this I'll get into how the construction, so I'll just state the results. And okay, so the second is if X is so X is an oblivious bit fixing source, K is n power K is n power delta, I think, yeah. And so f is the function of, so f is T local functions, the family of T local functions. So
Maybe different letters.
oh yeah, sorry, L. And so what this means is that, so this is the code word, this is C prime, and any output bit depends on at most L input bits. Right, so this is NC0, but the L we can handle is larger. It's is half minus gamma. So we get a corresponding non-malleable extractor for f, where f is in this family, uniform, comma this, and the epsilon is similar and T is similar as well. And finally, when X is oblivious bit fixing source, but with much larger entropy, K is n minus little o of n, and F is the class of AC0 functions. Then for any C in F, so AC0 is constant depth and polynomial size, ANDs, ORs, and NOT gates. So you get this. Sorry, let's just use F here. Epsilon close to uniform and this. But here the error is worse. It's log n, and T is, but for applications to non-malleable codes, it's not useful to get because the error is epsilon times 2 power T, so you do not really need these many to output these many bits. But
You get a code with exponential
Yeah.
stretch.
yeah, something like that. Yeah, quasi poly. Yeah. All right. So, all right. I think it's maybe time for a break if you have questions. Okay. So, let's start out by reducing the problem of constructing extractors for AC0 to local functions. And it's a very simple reduction, again, going through, if you have AC0, it's some kind of a switching lemma. So, okay, so.
Which construction will you show?
Yeah, so the construction I'll show is not one which is written on, so it's for low weight affine sources. And it's a homework problem after looking at it to come up with a construction for linear. Okay. So, yeah, maybe I should go through this quicker so that I can actually show some. So AC0 to local is, so you have a source X and where F is an AC0. So by the switching lemma, if we apply a random restriction on the source with, say,
But if you are
yeah.
explain, I don't know if everybody
Yeah.
knows about this. So
Oh,
either
that's
you,
switch. Oh, I see.
So either you
I
will
see.
explain it or you
Okay.
don't explain. I mean,
All right.
you can say there is a standard way to get from AC0 to local. That's okay
Right.
too.
Okay. But actually, yeah. All right. So, okay. So, since let me do this, and I'll not show the other.
Because the other things are more new. I mean, this
Yeah.
is like
This is yeah. Okay.
It's a very important thing to learn about. But if most people know about it, then it's not the new thing.
Right. Okay. So.
It's not Asta.
Yeah. Yeah, it just says, yeah. So, okay, there is a easy way of, there is a standard way of reducing from AC0 to local, and so it kind of, you go to lower entropy. You need local for smaller entropy, which will give you extractors, non-malleable extractors for AC0 for higher entropy, because you are restricting some bits.
This is how you go from 2 to 3.
Yeah, from 3 to 2. Yeah, yeah. And so also for local sources, there is a way of going from local sources to affine sources. So essentially, I'll just sketch the idea because it's simpler. Okay, so let's do local to affine. So X is an oblivious bit fixing source with some amount of min entropy. So there are some bits which, so let these be the active bits. By active I mean the bits which are uniform and independent, right? Because it's an oblivious bit fixing source. And so, and these are the output bits. Okay, the output bits of what, right? So let F be F is, say, L local. So these are the active bits of X and the output bits of f of X, right? You have this local function which acts on X and gives you n bits. So we can think of it as a bipartite graph where there are k nodes here, each node corresponding to one of the active bits, and n output bits. And the adjacency graph is just when some output bit depends on an input bit. Right? So since it's L local, you know that the degree of any right hand vertex is at most L. So the idea is, first you do some kind of a Markov to throw away vertices on the left which have too many neighbors on the right. And then, so for example,
So let's assume it's
yeah.
biregular.
Yeah, nice. Yeah, and then one can do this iterative process of, say, suppose these are the surviving bits. So start with one of them and go on the right and come back. So basically look at the neighbor of some vertex V, right? The set of all nodes on the left such that it shares a neighbor with this vertex. And essentially fix all those coordinates. So this ensures that this is the only bit which influences these output bits, right? So you can iteratively do this and
Do what?
okay. So we are starting out with a source X. And what we did was first made it biregular. So the other bits fix it, uniformly sample and fix. So we are going to convex combinations of X.
By regular.
It's biregular.
So you are allowed to fix more bits. This is what you're doing.
Yeah, exactly. Yeah.
So, but what are the parameters? What will K be here relative to N in this example?
Right. So if you start out with an entropy K source and do this process, so the process is this, that pick a vertex, go on the right, come back to all its neighbors, fix those things, except this, and keep doing it for the other things. And
So you just trying to find a large independent set in this.
yeah, and it's just a trivial thing that you do. Yeah,
Yeah, so a large independent set on the left.
Yeah. On the left. So the other, so it's just now a source on.
But in order to have anything surviving, you have to have the K very large compared to
Right. Yeah. Sure. Yeah. So, so if you do this, then you end up with a source with entropy. This is.
K is L, right?
Oh, sorry. Yeah. Sorry about the variables. Yeah. Right. And you sort of want this to be at least, say, n power delta for the reduction to work. So because we know, we'll see how to construct such for affine sources. So it's kind of saying that L is, so you get an upper bound on the locality that you can handle. So it's like what? Something of this. All right. Yeah, so this reduction is pretty easy.
But why is this affine? I mean, they may still compute the bits may
Right,
still
yeah.
compute an arbitrary function of the non-active bits.
Right, good. Yeah, so what we have done is change from L local to one local, right? And so one local is, it's easy to see that one local sources are, you can express it as affine functions, because so each bit is either, so you have this source f of x under this restriction where you have like some x1, 1 minus x1, and so on. So this can be like you have all these vectors corresponding to these variables and you just sum them up, right? So is this clear? So say you have x1, so the vector corresponding to this would be like, so you can remove these things out. So you just place ones where the x1s appear and add an offset. So right, so
So you say all you're saying is a function of one variable is affine.
yeah.
You're right.
Right. And the thing to notice is that, okay, so this form a basis for the affine source, and they do not have too many ones in them. So it's a good thing for us. So, all right, I'll remove this and now go to the main construction. Okay, so
now you're proving one.
yeah, so now I'll be proving something which is slightly different from one, but it's very easy to get. A slight change in one would give you this. So what we'll be doing is we'll look at, okay, so let's start out with defining low weight affine sources. So this was studied by Anup Rao in 2009, these class of sources. So it's essentially an affine source, X affine, and its weight is W if there exists a basis of X B1 through Bk such that the weight of each Bi is at most W, where this is the Hamming weight. So there exists a set of basis vectors which have low weight. So, and we'll be constructing non-malleable extractors for such sources, for low weight sources, against arbitrary affine adversaries. Where X is W min entropy K and A is any affine function, and so K is at least n power C delta for some large enough constant C, and the weight W is bounded by n power delta, and this works for any delta, and the error epsilon is n power omega 1, and the output length is n power omega 1 as well. So notice that the reduction that we saw from local to affine actually
It's weight 1.
exactly, yeah, it's weight 1. So right.
But it's big fixing.
Yeah. Right. All right. Okay, so now let's actually try to construct these extractors. So
if it's weight 1, is that a linear substance?
No, weight 1 just talks about the basis. So if you had the basis spanned by the unit vector, by the elementary subset of the elementary unit vector, with one single one somewhere, then it would be weight 1. But if it's generated by a basis in which every basis, some basis, which every basis element has
like if it's a
prime
chord,
non-zero,
maybe.
then it's weight 5.
Yeah.
So actually the reduction of both the bases is weight 1 and the affine transformation.
Yeah, but you don't really
Well,
need, yeah.
from both of them.
Yeah. So, okay, so we start out with X, which has these nice properties that it is bounded weight and has min entropy. And the first step is to apply a condenser to X. So to get a string V. Okay, so actually a linear condenser. Okay, so a condenser is a weaker function than a function which has weaker guarantees than an extractor, in the sense that the output need not be uniform, but the min entropy rate, which is the min entropy by the length of the source, increases. Right? So it turns out that for low weight affine sources, Anup constructed a linear condenser. By linear, it means it's a linear function of the source. So, and the linear condenser is just the parity check matrix of a good code. So, and it's not hard to see. So So if this is the parity check matrix, it's n minus k, and this is yours, the string x, right? And you output v, right? So this linear condenser is the function just takes the parity check matrix and multiplies out with. And roughly the reason why this works is that since x has low weight vectors, so x is essentially summation of, say, so if h is the parity check of and some n comma k comma d code, then essentially, so h of okay, and suppose x is like summation of alpha I bi, where these are the vectors, right? So this is the basis of low weight vectors, and these are the coefficients. I've used k too many times. Oh, the weight is w, so okay.
The parity check matrix, the subspace is orthogonal to all of your.
The kernel is the code. Kernel of this matrix.
Kernel,
has
yeah.
things of high rank.
Yeah. So essentially, all we are saying is that h of x will be non-zero for some subspace sitting inside x, which is of decent size, because the bi's have low weight. So if you look at say summation of I through d over the weight of each bi minus 1 of alpha I bi, then this is always non-zero. So it's essentially injective on this subspace, so it preserves the entropy. All right, so okay, so with this done, the advantage is, so we started out with an n comma k source, and now we have some n1 comma k1, where this is much shorter than k. So this is some k power gamma, say 2 gamma, and k1 is k power gamma, this kind of a thing, for some small gamma, which you can choose. Okay, I'll remove this.
Should think of gamma as bigger than 1?
No, gamma is small, it's very, very small. Like, yeah. Yeah, you want, so yeah, the main thing is, yeah, right, yeah. Okay, so the next thing is quite standard now, to convert this into a somewhere random source. So what that means is, take an extractor, and an extractor is called linear seeded extractor if for any fixing of the seed, the extractor is now a linear function of the source, right? So pick a linear seeded extractor and run it over all the seeds.
So just a second before, the condenser does not have to be non-malleable in any way whatsoever.
No.
That plays no role.
No, yeah. So, yeah. So the non-malleability stuff will now come in. Okay. So why are we doing this? So essentially, so any extractor. So the idea is, it's difficult to work with like n comma k source, and it's nice to work with the somewhere. And so a somewhere random source is like a matrix of random variables where you know that some row is uniform, but you do not know which row, obviously. And one standard way of doing it is by taking a seeded extractor and running it over all the seeds, because as we saw, in fact, for a strong seeded extractor, for most seeds, these rows will be uniform. Right. Good. And the point of first using a condenser is the fact that the seed length of a normal extractor is log n over epsilon, where n is the length of, say, x, right? And in fact, if you want to use a linear seeded extractor, then it's the best known ones are slightly worse. But anyway, so we can always, for simplicity, let's just think that we have a linear seeded extractor with these parameters. So if you run over all the seeds, then the number of rows is n power order 1, right? So instead of v, if you took x and ran over all the seeds, since the number of seeds would be 2, so this is the seed length. So 2 power d would be polynomial in n. So instead of doing this, first we shortened it to a smaller length source. And now by running over all this, we have much more control over the number of rows. So
Some linear in particular.
yeah, exactly. So
What
it's,
do you actually need? Some
so we
power
need
of k, some power of k to the gamma.
Yeah.
K to the c gamma.
yeah, exactly, yeah. So the number of rows is, as we said, it's k power c gamma, where again, so we have a lot of control over gamma, so you can always push it down below 1. All right.
This n is the old n, or it's now k to the 2 gamma?
Oh,
So it just, that's the reason
Yeah.
for
that's the reason for,
Okay, it's
yeah.
k to- okay.
Yeah. Yeah, so actually it's now n1, where, yeah. And another thing is, usually we like somewhere random sources which are fat, in the sense the rows are longer than the number of columns, because we know that some of the rows are uniform, and if you have longer uniform rows, it's better to, you can do a lot of things. So
They are not fatter than k to the gamma.
yeah, so here you have more rows than yeah, so this is actually a tall kind of thing. So to make it fat, there is a standard, I don't know if it's, but it's not very hard to, so we can take another extractor and get some more things out of x. So yeah, so this works essentially, so this would not in general work for any n comma k source. So this works because x is an affine source. So okay, so maybe I should go into the details of this.
So are you describing an oops form, or is
No, an ops work is just a linear extractor. Oh.
Yeah. So right, yeah, I think like these things have been used for like affine sources or some, yeah. So the thing is, so there is some function L of x. Yeah.
It's not clear. I mean, you're
Yeah.
not saying what you
Yeah.
did and what you. So here you have a
Right.
matrix. The output before you apply the second extractor, you have a matrix of random variables.
Right.
It has k to the c gamma rows. It has k to the gamma
Right.
width, and one row in it is guaranteed to be random.
Yeah.
That's all you.
That's, yeah.
So maybe
So
Yeah,
now if the row is close to k, you extract almost all in.
k to the
Okay,
gamma.
so
No, k,
Here
because
the
you
matrix
use another
is k
next.
to the gamma.
No,
You go back to x.
now what we have is like k to the say 1 minus some c prime gamma.
Before you apply
Before, yeah, we were saying about the first matrix.
the first matrix,
Yeah, before.
why don't you draw it and then draw the next matrix
Yeah.
that you have the parameters
Yeah.
there, and we will see.
Right, yeah, yeah,
Just all the dimensions.
yeah.
What you have.
So
So which
Yeah.
So the number of rows is k to the c gamma, and the number of columns is k to the gamma.
So now,
You apply, you use the role of matrix of as a seed for another extractor.
for another extractor, yeah. So it's
It's the same number of rows, but now the number of columns is close to the entropy of the original source X.
Right,
So
yeah,
about
it's-
K.
right. So this is this kind of. So it's a very much fatter matrix. And then the guarantee is again that by using properties of affine sources, essentially saying that this is an affine, this is a linear function of x, right? So, and it's short. So there is a linear x to this. So essentially x can be written as sum of two affine sources, a plus b, where b is independent of this because b lies in the kernel of this linear map. It's not.
So here the number of columns turns into the number of rows.
No, if
No.
the number of rows stays, it's k to the c gamma.
Oh, C
It's,
gamma.
nothing changes in the number of rows. We were just explaining why it's legitimate
Yeah.
to use these guys, the rows of this matrix, as seed to the source X, where they were generated from X. They are not independent from X.
Right. So
And
because
this is just because of linearity.
yeah, that's the yeah. Right.
So you need this to be a linear extractor and you need it to be an affine code.
Yeah. Right. Yeah.
Affine source.
Affine source and also the condenser, like V to be a linear function of X. All right. So and so we have not yet. So all this we are doing. There is also a corresponding thing going on in the tampered world. So. So similarly, we have produced a matrix L ext 2 of x prime L ext 1 of v prime s1 through right where oh, I see. So x prime is this f of x where
You called it A times.
a of x. And so any prime is like a of the corresponding variable. So now that finally our goal is to just get
No,
yeah.
it's not. V prime is not A times V.
Oh yeah. It's a combination of all these. Right. Right. Yeah.
But you apply the same process to X and to A.
Right. Yeah. It's yeah. Essentially, the function is inside, and then you apply all this. Yeah. Right. So now we need some heavy machine. So now the idea is essentially this, that you want to make all these random variables independent. I mean, yeah. So and then you could just take an XOR of these things. So if you could guarantee, so suppose there is a way of taking x here, similarly you take x prime here and apply a function some, so let's call it some correlation breaker of x and L ext 2 of all this long thing. And similarly for you do it for all the rows. And if you are guaranteed that these rows are independent.
So you're applying whatever it is to what? To the
To
inputs to the rows of the
Here, here.
So the rows of the matrix are already with the second extract.
Right, yeah.
So it's not written there.
Yeah, so it's
Oh,
yeah.
LX2.
LEXT2 of x comma LEXT1 of v comma s1, this kind of a thing. So you do it for all the rows, and if you can also guarantee that, so this kind of guarantees that these rows are independent. So for any, what it means by independence is, you know that one of the rows is uniform. So correspondingly, that row becomes independent of the other rows. And this actually has to ensure also that this row is independent of all the other rows as well. So, okay, intuitively, why would we expect that maybe, why would such a thing exist? So one thing is that the number of rows are not too many. So there is enough entropy in the system to make sure that you can actually do this. And such things, so these kind of functions are known to exist when, for a certain kind of structure, which maybe I'll make mention to make it much more clearer. So the cleanest way to state what, right? So consider this much simpler setting where you have, so I'm reusing some random variables, but it does not mean. So suppose you have two sources like this, and you have y1 through some yr. So what do you know is that x is an n comma k source, need not be affine, it's just an n comma k source. So this describes in a very abstract way what this ACB correlation breaker does. So suppose x is an n comma k source, and x is independent of the random variables z and y1 through yr. And further, you know that there exists j in some 1 through r such that yj is uniform. So there's this notion of correlation breakers in pseudorandomness. It's pretty useful now. That
what is reduced by Gil-Cohen.
Yeah, exactly. It was introduced by Gil-Cohen. That suppose you have a bunch of random variables which are arbitrarily correlated, but all you know is that there is some random variable here which is uniform. Then can you use some additional resource to break the correlation between these random variables? So this random variable, it's uniform, but you do not know if there is some other variable which is also the same as this, right? So it could be some variables just +1 of that, or there's arbitrary correlations in this random variables. So you have a bunch of random variables y1 through yr such that one of them is uniform, but they are arbitrarily correlated. Now using some amount of maybe a seed or some other additional resource, can you break the correlations between these things?
The amount of entropy in the random yi or yj is much bigger than r.
Yeah.
So it's like fat matrix like that.
Yeah, exactly. Yeah.
Do you mean them to be pairwise, non-correlated, or?
No, you do not assume anything. Yeah.
You just want that one coming from a uniform row will be independent of all the others after this process.
After the process.
Oh, okay.
So okay. So
Pairwise.
No, independent
Full.
of the
Yeah,
joint
yeah.
distribution of
So,
all the
yeah.
others.
Oh, the joint. Okay.
Okay, so yeah, let me write. So what you want is, so for simplicity, assume it's just 1 instead of j, it's 1. So it's what you want is the correlation breaker of x plus z of y1 conditioned on the correlation breaker of x plus z on y2 through the correlation breaker on x plus z on yr. So this is close to uniform, some L bits. So essentially, yeah, as Avi said, so this random variable in which you are guaranteed that there are uniform bits is independent of all the other random variables. It's just not pairwise. I mean, yeah, so the way we do it, you can just get pairwise, but you need to pay more to get this total independence. Yeah. And so this is, so here the amount of resource that we are asking is this, that you are just given access to one source in which there is some structure, but some part of it is correlated with these random variables. But there is some additive kind of thing which is independent of all this. So it turns out that you can actually use this to break the correlations between these random variables as well. So this was in a previous paper of mine with Shin, and so this kind of almost, so this affine structure here kind of shows that since all of this is like an affine function of x, again you can break x into say x1 and x2, where x2 is correlated with all this, but x1 is independent. Except that there are also the tampered variables which you need to take care of now. So there you need to supply this function with some kind of advice, and it gets yeah, I guess it will. So yeah, this is the high level picture maybe of, yeah.
We should take it as a black box that there is something like this ACB.
Yeah, so I don't know how, so right, so this ACB is, this correlation breaker is based on this alternating extraction kind of games. So I don't know, should I?
There's no chance
Yeah.
to
Yeah.
alternating extractor, you need 2 hours just
Yeah,
for this.
yeah. So yeah, but
So maybe just define what you need so that you can proceed. We are not done.
right. So okay, so okay, so maybe there is a sub problem which, so there is this notion of an advice generator. So yeah,
Maybe just tell us why we were somewhere. We were in this picture.
Right,
Not,
yeah.
It seems like we are almost done assuming something.
right.
So you have some magic function ACB
Yeah, so
that does something, and then assuming it is assuming. So tell us what it does. Assuming it does it, how it finishes the problem, how it
Oh,
gets there.
so
Because right,
yeah.
you just were going
Yeah.
to excel things.
Yeah,
That's
yeah,
it.
yeah.
So why don't you explain modulo complete assumption on ACB, how the final non-malleable extractor works?
right, so
Then,
yeah.
then you can explain whatever you
right,
want.
yeah, good. Okay, so this ACB almost almost gets you there, except the thing where now you also need to deal with, like, there are these primed variables, right, which was the problem. But again, maybe assume.
So let's give you an extractor, not an extractor first. But now you want to say that it's also non-malleable.
It's also non-malleable, yeah. So, okay, the thing is, I slightly cheated, and the advised correlation breaker takes a third input, which is essentially some identification of the random variable, like something which is distinct to it. So in this case, we could just put in one. So if we are just dealing with here, then we could feed in just the row numbers to the correlation breaker. So it would be 2 through R, right? But if you do this, then in the tampered world, like where it's x prime, z prime, and so on. So for the first row, it gets the same thing, 1, right, in the tampered world as well. Is this clear? So what essentially is happening is this y1 prime through yr prime as well, right? So this was, think of this as this matrix, right, y1 through yr, and whatever comes from x prime, v prime, and so on gives you another set of variables, right? So what the correlation breaker needs is a structure like this and an additional string which is unique to the random variable. If it's unique, then this guarantee holds. So the first idea is just pick the row number and plug it in. So you get 1, 2, 3, and so on. So then this random variable is uniform conditioned on all this and all this as well, right? Because its unique thing is 1, which is different from 2, 3, 4, or so on. But this random variable, the corresponding one, is not uniform condition on this because it gets the same advice, right? So the other, so from here, what do we derive? It's ACB of x prime plus z prime, y1 prime, and 1, right? So the advice is the same for both of this. So there's this magic box which needs different advice for different random variables to break correlations. And the way to get around this is through these advice generators, which, so till now we haven't really used that x and x prime are different. So to break this one business, you need to use that x and x prime are different. So one very maybe if you had so one way of maybe doing it would be like, since you know that x and x prime are different, encode x and randomly sample a few coordinates, sample using some extra randomness, right? So by encoding x using a good error correcting code, you have, so this is the encoding of x using a good error correcting code, and this is the ECC of x prime. So since you know that x and x prime are different by assumption, because we assumed it has no fixed points, so there is a large chunk of coordinates where these two strings do not match. And probably you could sample randomly a few of these coordinates.
You have no randomness.
Yeah, exactly. So yeah, so the actual way of constructing such a function is it's more trickier. So yeah, I think I could. So yeah, so assume that we do this, and we'll see if we have time to. So assume there is some way of generating some advice which distinguishes between the real world and the tampered world. Then you just attach it to this thing and hope that this correlation breaker still works. And once it works, then your output would be just as Avi said, it's just the XOR of these things, assuming you have independence of all these things. So
it's okay to take the XOR because one of them is random, so the XOR will remain random after the breaking of correlation.
exactly.
Since it's independent from the
Yeah.
other one,
Yeah.
by assumption.
Right, it's independent and it's also uniform. So yeah.
But you didn't explain how.
Right, yeah. So yeah, we could get into the advice generator, but I don't know if people are hungry or yeah.
This is where the non-malleability comes from.
Right,
It's the
yeah.
advice generator
Yeah.
combined with the
The correlation breaker, yeah. Yeah, yeah. At some point, you need to use that actually x and x prime are different. So, Avi, should I?
Yeah, probably, it's a good time to stop.
Oh,
So
okay.
if you want to say something about, what we missed or what are
Okay.
buzzwords we should learn about.
Okay, so I could pose it as, so the advice generator is a very like a separate problem to state, which, so these things are much weaker than non-malleable extractors, but all this correlation business kind of shows that if you can accomplish this weaker task, then you can actually get non-malleability. And so in general, so all you need is from x you this some advice generator of x is some string, and from x prime this is some function that you're applying, and all you need is that this is these both are so this is, so you need w is not equals to w prime with high probability, and right, or parts of, yeah.
Function is deterministic.
Yeah.
And the length is shorter.
Yeah, exactly. Yeah, that's one thing, because I mean you could always output x and get this guarantee, but you need something much shorter. So, for example, if the thing I pointed out here, if for example this thing had access to some extra randomness, then you could actually do this, right? You could encode x and then sample a few coordinates. So
how long do you want this thing to be? Constant length? Or?
No, so it's log 1 over epsilon. Yeah. So here I could tell you what the function is. Maybe you guys could try to prove it. So if it's x, then no. So yeah, so encoding is one of the paths. So also assume that you have access to these rows, right? So one of them is uniform. You want the uniform thing to be at least different. You don't really care about the other rows. So you have some x and some r, and you know r is uniform. Then what you can do is you can take a small slice of r, call it r1, another slice r2, like there are small chunks. And then, so your advice would be r1 with r2 with, you encode x and sample using r1, encode x using a good error correcting code, and then use a linear seeded extractor on x with an affine extractor on r2. So it turns out that so essentially plugging r1 and r2 in is kind of saying that the corresponding r prime variable, you have r1 prime and r2 prime. So if these both are different, then you're already done. So that's why you put the prefixes in. So this is kind of saying r1 and r2 are the same. And then it's, so yeah, this here to show why you exactly need this one.
So you pick one row, one specific row?
So you do it for all the rows, and so this kind of shows that for the row which is actually uniform, it will go through.
Why do you need an affine extractor on R2? This
Because
only about the case where it's uniform.
Oh yeah. Oh, for this case, yeah, you don't actually need it. Yeah. So, yeah. So, right. Yeah, there are in the sampling extractor. I think you need it. Yeah. So, so the intuition is this, that if r prime does not steal too much entropy from r1, then this should hold, and if it actually right, yeah. So, and in the other case, this should hold. So, So each of them is yeah,
Second extractor will just output a few bits.
yeah,
No,
yeah.
but even if it was 1 bit, you have 1 bit to explore.
No.
Oh,
This
but
is
the
done
number of
per
rows
row.
is
This
number of
per
rows
row.
is k per gamma. So
Ah, this is done per row.
Per row. The,
Ah,
Yeah.
so
the
that
device.
Ah, the advice is per row.
Okay.
Yeah.
So,
yeah, all right.